Okay, so now we're going to do this hardest problem incorporating bearings. Now, this is a very important problem. It'll show up in a very important place for you coming up here soon. It says a ship leaves port at noon and heads due west at 20 knots, a nautical mile per hour. At 2 p.m., to avoid a storm, the ship changes course to north 54 degrees west. Find the ship's bearing and distance from the port of departure at 3 p.m. So the first thing I'm going to do is I'm going to draw a line due west from our port. Now, this ship is traveling at a speed of 20 knots. That's 20 nautical miles per hour. So in order to know the true distance traveled here, what you have to do is you have to think about how many hours they're traveling at this speed. So if I'm starting at noon and I'm going to 2 p.m., that's 2 hours. 2 hours where each hour is 20 knots. Each hour is 20 nautical miles. We take 2 and we multiply it by 20 to get that they traveled 40 nautical miles. So I'm going to put a 40 on this line. They traveled 40 miles, not 20. Then from here, they changed course because of a storm at a bearing of north 54 degrees west, meaning at this new point where they stopped, where they changed direction, I have a new coordinate plane with that point at our center, where this is north, east, south, and west. So if they changed at north 54 degrees west, that means from our north line we go 54 degrees towards the west. That is over halfway. This angle is 54. And it wants to know the distance they fully traveled and the bearing from the port of departure. So it wants to know the length of this line. Oh gosh. The length, no, why'd that go like that? The length of this line and the bearing from the original port to where they ended up. So this angle right here. Now it also, I forgot to label the distance on the last leg of their trip. They changed direction at 2 p.m. and ended at 3 p.m. That's only 1 hour, meaning they only traveled 1 times 20 nautical miles. So, on this picture, on this diagram, there is not a single right triangle. And it may be hard to figure out, okay, we're trying to solve for the length of that purple line. We'll call that, let's change this to blue. We'll call that purple line our x value. And we're also trying to solve for theta. So we're trying to find a right triangle that has x, that purple line, that full distance, as one of the sides on the right triangle. And theta is one of the angles in the right triangle. The only way to create a right triangle that has those two values is by taking where we ended up, where the ship ended up, and drawing a line straight down to our x-axis. This creates this big right triangle. Now, unfortunately, on that big right triangle, all we know is that part of the base is 40. That's all the information we have. But if I first find the height of the smaller green right triangle, that will also be the height on the bigger right triangle. We'll call this y. And then if I find the base on the smaller right triangle, we'll call that z, we will know the full base on the bigger right triangle. Now right now we don't have an angle inside of the green right triangle, but we know that that 54-degree angle and this angle right here create that quadrant 2, create that 90-degree angle. So to get this green angle, we just do 90 minus 54, and we know that this is a 36-degree angle. So we're going to have to solve for two things here. We're going to have to, well, more than two things. First, we're going to have to solve for two things. X, or y, and then also z. Whoa. So, first let's solve for y. Theta is 36. Well, I should call it alpha. We have a hypotenuse of 20 and an opposite side of y. So O and H means we are using sine here. Sine of 36 is O, which is y, over H, which is 20. To get y by itself, we multiply both sides by 20, and we have 20 times sine of 36. 11.5, nope, 756. Then we solve for z. Where z is the adjacent side this time, so I'm going to use cosine. You could have used Pythagorean theorem as well, but I prefer trig, so I'm just going to keep using trig. We have cosine of 36 is z over h, which is 20. So z is equal to 20 times cosine of 36. .180. So now I know that the full length here on the big right triangle is 16.180 plus 40, which is 56.180. So now I could either solve for theta and then use trig to find x, or I could just use Pythagorean theorem and solve for x, which I think that's what I'm going to do. Solve for x first by doing Pythagorean theorem. For my a value, I'm going to have be that bottom side 56.180, and my b value be y 11.756. And to get my hypotenuse by itself, I have to square root these. So I have the square root of, and I'm going to go up and get the 56 value, and parentheses square it, plus parentheses scroll up and get the y value, enter to bring it down, and square it. And I get 57.397 is our x. Now that's the distance from the port of departure, and that's 57.397 nautical miles. That's what we're first solving for, is the distance. Then we also need to solve for the bearing. Now I'm going to use trig, and I'll use the 56 number and the y number 11.756. The 56 number is, according to theta, our adjacent side, and according to theta, that y value is our opposite side. So I'm going to use tangent here. Tangent of theta is opposite, which is that 11.756, over adjacent, which is the 56.180. And to get theta by itself, we multiply both sides by the inverse of tangent, or we take the inverse tangent on both sides, I should say. They cancel, leaving me with theta is equal to tangent inverse of 11.756 over 56.180. Now I'm going to always pull these numbers from my calculator, go up and get the 11 number divided by the 56.180 number. And I get 11.819 degrees. However, it wants this written as a bearing. Now this part is a little tricky because right now that bearing, that angle, is not from a north or south line. It is closer to the north line. So I am going to draw a little north line. And what I actually have to do is I have to subtract the angle I found from 90 to get this in bearing form. So I'm going to do 90 minus 11.819 to get that this angle is 78.181 from the north line. It does not look like an N, I'm so sorry. From the north line to the west. So I put an N in front, 78.181 degrees to the west. And that's my bearing. This is by far the hardest problem, but it will be showing up in an important place coming up.